Okay, let's get started. So do we have a question from this time? If not, then yeah, let's continue our slides on quantum mechanics. And yeah, the scope is also some part of the book is chapter 2.2, 2.3, and also one of the protocol is from chapter 1. Okay, and let's go over this POV management idea once again. Okay. Yeah, so we go over POVN last time, but it was not very clear, so let's see this again. So the idea of POVN is that it's I guess it's a less informative version of a measurement. So the idea is that when you think about doing measurement, and so you have some generalized measurement that is described by the set of measurement operator, then you know that the output probability of some outcome I is this and mi dagger mi sandwich between your side. And you see that this thing doesn't this thing only depends on mi dagger mi. It's kind of like mi squared. So we see that if we don't care about the post-measurement state, then when we only care about this post-measurement probability, then we don't need to really know what mi is. Instead of knowing mi, we can only know those ei that are equal to mi dagger mi. And then you can just write down the output probability, or excuse me, the outcome probability as this psi ei psi. Okay, so if you are not recording mi, instead you only record the ei, then you can still know what are the output probability. Okay, and so why do you want to do this? This is just less information, and you're still recording set of matrices. It turns out that sometimes this was simplified notation, because a lot of time you don't really care what the post-measurement state, because you only do a measurement and you are not going to use that state to do anything else. When you only care about the measurement probability, then writing ei down is easier than writing mi down, because for example, when you will just see this equation is simpler than this equation. You write down mi, you need to write mi dagger mi for your probability. If you write down ei, you need to write ei here. Yeah, so that's basically that. When you only want to calculate probability, then writing ei is easier than writing mi dagger mi. Okay, and yeah, and we can generalize this idea a little bit. So from here, it's pretty easy to see that for every set of measurement, you can get a set of ei. You just write every ei equal to mi dagger mi. And actually, you can just write the ei, and you know that it will correspond to some measurement. Okay, so if you just start with the set of ei, and so how do you know they are good POVN, meaning that they correspond to some measurement? Okay, so the set of matrices ei that will be a POVN, they need to satisfy these two properties. So first one is each ei need to be positive, or more excuse me. So more precisely, each ei needs to be positive semi-definite. So the eigenvalues need to be all greater than or equal to 0. Okay, or it's called positive in a textbook. And the second one is summation ei equal to identity. And you can kind of see this summation ei equal to identity come from the probability need to sum to 1. Because when we say we have a POVN that's given by this set of matrices ei, then you measure this POVN on state side, and then each outcome is probably psi ei psi. And it's pretty easy to see that this completeness relationship here. So summation ei equal to identity guarantees that this probability equal to 1 when you sum over oi. Okay, so yeah, any set of matrices that each one of them are positive and they sum to identity matrix, then it's POVN. Okay. And obviously, as usual, we are sloppy on the dimensional matrices, but you can imagine that these matrices need to be square matrices, and they need to have same dimension, and the dimension also needs to be the dimension of your state. Okay, so yeah, that's some implicit dimension assumption we make. Okay, so yeah, so this set of matrices are called POVN, and each one of them is called a POVN element. So it's kind of like a measurement. So the set of matrix, the set of those mi together is called a measurement, and each mi is called a measurement operator. Okay. Yeah. And so far, question about definition of POVN. Okay. And yeah, so we say this is kind of easier definition of POVN, and it makes sense because it's kind of like having a correspondence between measurement and POVN. And so it's pretty easy to see that every measurement can be mapped to a POVN. So every measurement has a POVN. You just write the EI equal to MI dagger MI. That's the motivating example we have here. And so we can quickly check out those two conditions met. And so MI dagger MI is a positive operator. Pretty easy to check because intuition is like it's a square, but you can also sandwich it between any vector. Then you see that, okay, so let's write down that a little bit. So it's easy to check that when you, this is a positive operator, this is a PSD operator because you want this thing sandwiched between any I to be greater or equal to 0, okay? And you see that this thing equal to just a known square of mi psi, okay? And okay, sorry, this is a little small here. This thing is the known square of mi psi, known square of mi psi because this part is the dual of mi psi. When you dual mi psi, then you put psi to psi bra and mi to mi dagger. So it's a dual of mi psi times mi psi. So that's the known square of mi psi, and that should be greater or equal to 0 for psi. Okay, because this is one vector, and the known square of any vector is greater or equal to 0. Okay, and so you see that EI is a positive operator, and then the second. Then the second property just comes from the completeness relation from the MI. So summation EI will be summation I MI dagger MI, and we know that's identity matrix in the definition of measurement. Okay, so every measurement they can be mapped into a POVN. You just have EI equal to MI dagger MI, and also every POVN kind of valid for some measurement because there is some measurement such that EI equal to MI dagger MI. Okay. And yeah, it's basically you taking the square root of EI, and then you can take, if you have MI equals square root of EI, then MI dagger MI will equal to EI. And but EI is a matrix, so you need to work a little harder to define the square root of a matrix. But for positive matrix, you can define that, and you can find the MI. Okay, and yeah, and but we need to be a little careful here. So you think. From those two kind of things, maybe EI and MI are one-to-one correspondence, but actually not. It's many-to-one correspondence. So because you kind of taking a square here, so there are many different MI that will be make to EI. Okay. And anyway, so EI is like MI with less information, but easier to use in notation. And let's go back to this example once again. So we want to use 3-outcome POVN to do the state these two state distinguish problem. So we want to distinguish whether our unknown quantum state input is a 0 state or a plus state. Then we can do this 3-outcome POV and E1, E2, E3, and yeah, E1, E2, E3, and just as we say, we know those 3 POV elements. Then we can know the outcome probability. So we can know when 0 is the input, what are the outcome probability 1 to 1, 2, 3, and when input is plus, what are the outcome probability 1, 2, 3. And here the spatial design we have the outcome is the first outcome E1 is proportional to the projector onto one state, and E2 is proportional to the projector on the minus state. So in particular, we know that 0 cannot project on 1, and and so we know when the input is 0, the outcome must be 2 or 3. And similarly, when the input is plus, the outcome must be 1 and 3. And so we do a bit of a reverse logic. Then we see that when we see outcome is 1, then the input must not be 0, so the input must be plus. And similarly, when the outcome is 2, the input must not be plus, and so input must be 0. Okay, and yeah. So we see that when we have getting outcome either 1 or 2, then we make no mistake. This is what we mean on the left side here. So we see 1 or 2, then we perfectly distinguish, not perfectly, then we are safely to say we are from plus or 0. Okay. But the catch here is that we are not perfectly distinguish between 0 and plus. We know it's not possible because there is also outcomes 3. And when it's outcomes 3, this basically has the same probability from 0 and plus, and we know nothing about whether input state is 0 or plus. Okay, so that's a small recap on POVM. Anyone has question? If not, then let's go to the composite system. Okay. And we kind of already talked about this in our postulate, but let's open this up a little bit. Okay, so the question is, and as we said, this is something implicit in the postulate of quantum mechanics. People just think this is true, but I think a lot of time people want me to write it down. Okay, but here we are opening it up, and it's nice. And the question is, when we have several quantum system that, we have a quantum system that's made up of several different systems. Okay, so it's a composite system, and they have more components, so two or more distinct physical components. And so how do we describe this composite system? And we know we describe quantum system by what are the state space and what are the transformation and what are the measurement. Okay, so we need to write what are the state space and the transformation and measurements. Okay, and I guess not just look at it, I found out that we are not totally complete. Okay, but anyway, so the state space is the tensor product. So all of them, the answer to all of them is tensor product. Okay, and anyway. So the state space is the tensor product of all the state space together. Okay, so if you have the Hilbert space H1, H2, H3 for each individual system, then the state space is the tensor product of all of them. And in particular, so if you have if you prepare each system in a particular separate state, okay, so each system is prepared in state psi 1, psi 2 to psi n, then the joint state is psi 1 tensor psi 2 tensor psi n. Okay, and yeah, so we are now talking about kind of what happens when you do individuals into individual system. And so if you do a unitary on one of the system, okay, so say you do unitary on system A, so maybe A equal to 2 here. So you do a unitary U on this H2, then the corresponding unitary on the whole Hilbert space is the identity tensor U tensor identity tensor identity tensor identity. Okay, so it's whatever unitary on your system and tensor identity on all other systems. And but this is what happens when you only do unitary on one system. There can be also entangled, what we call entangled or interacting interaction transformation you can do on the whole system, and that will involve two or more subsystems. Okay, and yeah, and similar to unitary, you can also do measurement on one subsystem, and then that measurement will have a measurement operator that is mi on your system, on your subsystem, and the tensor identity on all other places. Okay, and obviously you can also do joint measurement on the different part of the system. Okay. And then there is a little notation that's very similar to what we cover in our mathematical chapter. Okay, so in our mathematical chapter, we talk about those notation of tensor product, and and we'll be lazy sometimes. And here we are being lazy. So as we said here, we said the state will be tensoring altogether, but we might be too lazy to write this tensor here. So we can just omit the tensor because this is not too ambiguous, because there are no other way to multiply basically no other ways to multiply two column vector together. So instead of writing psi tensor phi, we just write this psi phi together, and this means psi tensor phi. And sometimes we are even too lazy to write down the middle part here, so we just write this psi comma phi. Sometimes this gets confusing, but usually it's okay. And sometimes we are even more lazy than writing the comma here. sometimes we are even too lazy to write the comma here, so we just write the sci-fi. Okay, and yeah, so those are the notation you might encounter that that means tensor product of quantum to quantum state on two systems. Okay. Yeah, this notation can be get ambiguous sometimes, but usually it's okay. And and then there are also notation for tensor product between matrices. Okay, so now this one is even more fishy. So we have n tensor B. So this is tensor product of two operator or matrices on two subsystems. And so A will act on system A, and A will act on first system, and B will act on second system, as we know from chapter 1. And then if we label our system as 1 and 2, sometimes once again we don't want to write tensor, then we just write A sub 1 and B sub 2. Okay? So this means A on subsystem 1 and B on subsystem 2. And sometimes you will see very lazy notation that you just write A1, B2 as AB, and so this is really ambiguous. This is base notation, but sometimes happen. I just write here so that you have your warning here. But I think we should avoid this because you don't know this is A times B or A1, B2. Okay, so this one is really confusing, but sometimes it happens. Hopefully we didn't use that. Okay, okay. So those are just notation. Now let's talk something more about the consequence of the composite system. And now we go to this famous topic of quantum mechanics that's called entanglement. Yeah. And this is something also kind of going to in chapter 1. Yeah. And the idea is that so we have our postulate of a composite system. Okay, so this postulate here, we say the Hilbert space of the composite system is the tensor product of all the individual Hilbert spaces. Okay, so okay, so the space is a huge tensor product space. It has a huge dimension, and we also remember there is a small thing that we write in parentheses in our postulate 1. Postulate 1 says that the state vector is described by a unit vector in a state space, and then we have this small parenthesis says that actually this kind of a reverse is true. So any unit vector in our state space is also a valid quantum state. We think this is true, and actually this is something. This parenthesis here, you guys physicists is called a superposition principle. So physicists have believe in this principle that every superposition of a quantum state is still a valid state. That's how you get that every vector is any unit vector is a valid quantum state. Okay, and anyway, this is something you believe in. So any vector in the Hilbert space is a valid quantum state, and so we have the superposition principle here. And now we think about it in composite system. Then we find out that there are entangled states. This means that because we find out that every state in tensor product of Hilbert space is also a valid state, and there are entangled states that's not a product state. Okay, so we think about there are H1 tensor H2, and this is a huge space, and yeah, so there are these weird entangled states. So we have an example here. Okay, so what's an entangled state is that a state in a composite system that cannot be written as a tensor product state of a component system is an entangled state. Okay, so for example, we have a psi that's we have an example state psi that's 1 0 plus 0 1. Okay, so the notation here we are in the most lazy notation here. So 0 1 here means 0 tensor 1, and 1 0 later means 1 tensor 0. So we are in a 2-register system, and each register is here we are in a 2-register system. So let's write a lot of notation to say very little. Okay, so H equal to H1 tensor H2, where each one of them is a qubit. So H1 is a qubit is C2, and H2 is C2. Okay, so those are qubit. Okay, So our state is a 2-qubit system. So a qubit is a 2-dimensional space, and this H is a 4-dimensional space. And this 4-dimensional space, so just a little review. So this 4-dimensional space is equal to span of its computational spaces. So it span over 0, 0, 0, 1, 1, 0, 1, 1. Okay. And this 0, 0 means 0 on first system, tensor 0 on second system, and 0, 1 means 0 on second system, tensor 1 on second system, and etc. So 1, 1 is 1 on first system, tensor 1 on second system. Okay, so we have those 4 states, and this is a linear space. So now we use our superposition principle, and it says that any unit vector in this 4-dimensional space is a valid state. So we can have a vector that's 1 over square root 2 over this 0, 1 vector plus 1 over square root 2 over this 1, 0 vector. Okay, and yeah, so this is a unit vector in this 4-dimensional space, and by our superposition principle, this should be a valid quantum state. Okay, so this should be a valid quantum state of this H1 tensor H2 system. And we find out that it's entangled, and this is something that you can prove yourself, and maybe we will even put this in homework. You can prove that this state is very different from this 4 state that we write here. It's very different from this 0, 0, 0, 1, or 1, 0, or 1, 1. Because you cannot find any state A, B. So for any state A or B, A in H1 and B in H2, their tensor product will not equal to 1, 0 plus 0, 1 over square root 2. Okay, so this is an entangled state. You can prove that, and yeah, and it's really something weird. You find out that it's kind of like you put 2 quantum systems together, then you find out that the possible state is more than what you can have then separate in a different place. Okay, so A are all possible states in H1, and B are all possible states in H2. And somehow we put the 2 quantum states together, they have some correlation, and you have even more state. You can have this entangled state that's not just first state, a state on 1 tensor a state on 2. Okay, so this is really well, this is a very quantum phenomenon. Okay, question about entanglement? Yeah, if not, then let's go to a bit of long proof. Okay, so the next topic is an example of using composite system, and we see, I guess is example of what we can do on a composite system, and what we want to show is that generalized measurement can be gotten from projective measurement. So this is kind of finish the story on our measurements. Okay, remember we talked about the 4 measurement, 3 different measurements, and actually that formula. So we have our computational basis measurement, and we have our So the story was that first we have computational basis measurement, then we have also normal basis measurement, or also normal basis measurement, and we have measuring operators, and then finally we have the generalized measurement. Okay, and it's easy to see that each one of them is generalizing general. Okay, each one of them is more general than the previous one, but we also claim that computational basis measurement has the same computation power as other things. Okay, so that means we claim that computational basis measurement can be used to do all of them. And here we kind of get the proof by showing that you can use computational basis measurement to get this most generalized measurement. Okay, yeah, and okay, so we are going to use computational basis measurement to get a generalized measurement. And the trick is you also need to do some unitary before you do the computational basis measurement. And we also need to use composite system because we are going to introduce what we call the ancilla system. Okay. Okay. And yeah, so let's start. Okay, so we want to do generalized measurement. So and we are using composite systems, so we are going to give our systems our names. So so we can distinguish where we are acting on. Okay, so we start with our quantum system that we measure. It has a state space or Hilbert space Q, and we want to perform a measurement that described by those operator big M sub small m. Okay, so those are several operators where the outcomes are labeled by this small m. Okay, and as we say, we use a composite system. So what we do is we got to introduce another system. So we have an ancilla system, and we call it M. Okay, it's a little confusing, but this is the notation we choose. So this M has no relation with this M. I guess there is a little relation, because this M also means for measurement. But anyway, so we have but this space has, so they have the same origin of their name, but really this space this big M is a totally different operator from those big M sub small m. Okay, so it's a little confusing, but big M sub small m are measurement operators. Those are matrices. And this big N is Hilbert space. This is a linear space, so it's a totally different object. Okay? So we have a linear space here, and we have a whole bunch of operators here. Anyway, so we introduce this linear space big M here, and well, this linear space has some orthonormal bases, and once again, it's an overloading of notation. So this is actually not overloading notation. So we have the orthonormal basis that are labeled by small m, and and this small m is actually same as this small m, because we want the number of basis elements here to same as the number of measurement outcome here. Okay, so this this ancilla system is where we are going to basically record our measurement outcome. Okay, so it has this orthonormal basis that has the same number of elements as the number of elements in your measurement set. Okay, so it has 1/1 correspondence. So this small n is same as this small n. Okay, and yeah, so there is this ancilla system that we want to implement. And for now, we kind of think it's easier to think about physical. Okay, so we think this ancilla system. However, ideally, it can be implemented physically. So there is an extra quantum system here. Okay. So we just have this extra quantum system that we can have, and it will interact with our original state space. Okay, and we want this system. So you will ask your engineer or experimentalist to design this system that has this property where you can find also no basis inside that has same number as your measurement operators. Okay. And yeah, so we introduced this ancilla system, and now we have this picture here, so we kind of think our system like this. So we have our original system to be measured, and then ancilla system that help us do the measurement. So our quantum system is larger. So our quantum system is now this Q tensor M. Okay, and now we kind of think about what we want to do. Okay, so this is just a small iteration here. Remember, we want to do measurement n sub big N sub small m on this state side, and so the outcome should become big N sub small m side, and with probability being this vector squared. Okay, and excuse me, we have little typo once again. Okay, and psi squared. Okay, and yeah, and so as we say, so if you still remember, as we say, we want to, what we want to do is we want to do some unitary on both systems. Okay. So we want to have some big unitary on both systems. So it will make the two systems entangled and correlated in some way. So apply some unitary on both of them, and then we will do measurement on our small m. Okay, and so what does this unitary look like? So this unitary will depend on the measurement you want to do. So the unitary will depend on this set of n. And in particular, so this unitary want it to have this property. you want that this unitary acting on the starting state we have here. So starting state here we have this psi and 0, so psi tensor 0, and we want it to become sum over m, m psi and tensor. This is a little confusing. Yeah, so we want it to be summation m psi tensor m, okay, and this whole thing summation over m, okay, and yeah. And kind of the intuition here is that because we want the post major on constant to get this m to be this m psi, so we want it to become m psi on this system. Okay. Yeah, so later we'll check that if we have a unitary do this, then after you got this, you do measurement on this big M system, then it's enough to get generalized measurement on your Q system. Okay, and but before we do that, we want to argue that this U exists. Okay, so we hope this U exists. We want this U to do this thing. And but first we will need to check that we actually have a U to do this thing. And here we kind of yeah, so we want this U to have this property. So this weird equation here. So maybe let's highlight it. Okay. So U will want to satisfy this equation. U on the initial state psi 0 equal to sum over small m, big M sub small m psi tensor small m. Okay. So you see that this is a very usually very entangled state. So once again, it's an entangled state, so it's an m psi tensor small m, but the sum over all the different small m. So here the summation over small m is over all possible outcome. Okay. So want U to do this thing for us, it turn your initial state to this state to be measured, and we also want U to be unitary because we know all quantum operations are unitary, and yeah, we also kind of assume that all unitary are possible quantum operation. Okay, and yeah, so U is we want U to be unitary, and here we don't do the whole proof that this U exists. We do kind of sanity check. Okay, so you want to satisfy this equation and want it to be unitary. Okay, and we know that if U is unitary, then U preserve inner product. So we kind of check whether U preserve inner product on different state, on different starting state. Okay. So different starting state means that we have a different state to be measured on Q. Okay, so maybe there is some state psi to be measured on Q, and there is some state phi to be measured on Q. And we check that U preserve inner product between the psi tensor 0 and the phi tensor 0, because we know so. And yeah, so we check it here. So inner product between these two things. So we take a dual of this and then multiply on this. So dual with this thing, dual on this thing is okay. Actually wrong. Excuse me, another typo here. So but our notation is should be okay. It's a little wrong register. Okay. Okay. Yeah. So I should write. Phi 0, and yeah, because this thing dual, and because we say dual doesn't change the order of all registers, so it should be phi bra and 0 bra, and this and then U dual is U dagger, and then multiply on this thing, then U phi 0. Okay, and so this thing. Inner product between this thing and the next one should be correct, and yeah, so we apply this equation on both of them. Okay, and so this U phi U phi 0, then that's by definition here is a summation m, and m phi and phi and n. Okay, so here, sorry, it's another typo. So it should be m phi on and tensor this m, and and then u on psi 0, it should be similar thing. It should be sum over another m prime, and here should be m prime. Excuse me. Yeah, and here should be m prime, and yeah. So I guess let's write this thing here. So this part, it should be summation m prime. So this thing taking dual, and some phi and m dagger sub m prime, and tensor over m prime. Okay, and yeah, so it should be and so we have this thing inner product with this thing, and we know inner product work on each slot, and it's also linear. So everything is linear, so we can put the summation outside. So summation is just summation m and summation m prime, and then we just have tensor product of one thing multiplied tensor product of other thing. So by our rule, it's the first thing multiplying together times the second tensor, the second thing multiplying together. And the first thing multiplying together is this phi m dagger sub m prime, and m sub small m psi. Okay, so this is the first register. Then we have the tensor second register is m prime inner product with m. Okay, but second register is just a number, so we don't write the tensor here. Okay, so yeah, a lot of calculation here, and sorry for the typo. Okay. And so we have this thing as the inner product, and then we do more simplification, and we know that those small m. Now we use this assumption that those km are also normal basis. So m prime and m are equal to each other only when m prime equal to m. So we can get rid of the summation m prime because only m prime matters is when m prime equal to m. And yeah, so this m prime m inner product is get rid of summation of m. So summation m prime. So we have summation m, phi and dagger sub m, and m sub m phi. Okay. Okay. Because m prime must be equal to m for this to be non-zero, and when m prime equal to m is equal to 1. So we just change every m prime to m, and get rid of the summation of m prime. And finally, we use that m dagger sub m dagger. Those are so those are measurement operators. So we can move the summation m inside, and use those things sum equal to identity. And so this is just inner product between phi and psi. Okay. Any questions so far? Yeah. Yeah, this is a much more complicated calculation than kind of expect. Okay, but yeah, this calculation can be done by you see that we use all the tensor product rules to do this calculation, and yeah, and the end of calculation result shows that our definition of this u on our psi 0 makes sense, because it preserves inner product on every possible side, on psi 0 for every possible side. So inner product being psi 0 and the phi 0 is preserved. So because the inner product of those two was this phi inner product with psi. Okay, and you see that after applying u, you still get this psi phi inner product with psi. Okay. And yeah, so inner product is preserved where u is defined, because for now we only define u on those states that has a form psi tensor 0. Okay, and then it's a homework problem, or not sure, we might or might not put this in homework, but this is some homework problem you can do, and you can show that if u preserve inner product on this space, then you can, so this is actually a subspace on your Q tensor of M, and if U is preserve inner product on some subspace, then you can always extend this U to to a full unitary on the whole subspace. Okay, and yeah, so we kind of omit another part of proof to the homework, and then we can let this U exist. Okay. Okay, so that's a lot of computation on this weird measurement relating unitary U. Okay, and for this U, and so that's this U, and we now kind of prove that U exists. Now back to our measurement. So we apply this U on our joint system with the psi tensor 0. And we'll get this state that we kind of want this summation m sub m psi tensor small m. Okay, and now finally we can do our measurement. So what we do is this state we do a measurement on the m system, and that particular measurement we do a computational basis measurement on the on the subspace m, and okay, so. This thing is actually comp basis measurement M. Okay, and yeah, so so computational basis measurement has a measurement set of measurement operator that those projector on your orthogonal basis small m. Okay, I guess we also assume this we also assume this small m basis is just a computational basis that we pick for system big M. Okay. But anyway, so the computational basis measurement has a measurement operator that's projected onto those m's, and small m directions. And as our postulate say, then this measurement on the whole joint system will have operators. We'll have measurement operators that are just identity tensor the measurement operator that's on the small m, that's the projector on small m. Okay, so here we use so let's go back a little. Use the measurement part of our postulate. So we say on the system big M, we have the measurement operator that's the projector on small m. And on the joint system, the measurement operator will just be identity tensor those projector onto small m. Okay, so we have so we have those measurement operator. Okay, and finally we apply our measurement rule on this joint system Q tensor m and see what are the post measurement state and the measurement outcome. Okay, and the measurement outcome probability. Okay, and well, measurement outcome probability. We have sorry, another typo. I'm missing a K0 here. K0. So measurement outcome probability, because this measurement is actually projective, so we don't need to write Pn dagger Pn. Okay, so because the Pn dagger Pn just equal to Pn. So this is projective measurement, and so the outcome probability is just your measurement operator sandwiched by your state, and your state is your u psi 0. Okay, and you took it to other side, and it's psi 0 u dagger. Okay, and yeah, then we expand our u psi 0 to by our definition, and the state is this. Sum. Now we need to sum over two different dummy variables, okay? Because we have for every time we apply u on psi 0, we have the dummy variable sum over small m, and but that small n is different from this small n, so we need to sum over m prime and m double prime, okay? So we have sum over m prime for this first for those bra vectors, so sum over m prime. And psi x by m dagger sub m prime and tensor m prime, and then the later part we have m double prime big M sub m double prime on psi tensor m double prime. Okay, And so this summation with n prime was here, and the summation with n double prime was here. But everything is linear, so we can put the summation outside, and we have those things inside. And now everything is a tensor product with each other, so we just deal with each register separately. So first register, we have the psi and the m dagger sub n prime, and times iq, and times n sub n double prime psi. Okay, so this is the first register. And the second register, we have n prime. Okay, so I guess we are skipping a step here. Okay, so the second register was is n prime, inner product with m, and m, and inner product with m double prime. And once again, we use that m is also normal basis. So it means that those inner product are equal to 1 only if only equal to 1 when n equal to m double prime and m equal to m prime, and also equal to 0 otherwise. So that means m prime must equal to m, and m double prime must equal to m. And yeah, so we can just get rid of this and say that n equal to m prime equal to m, and n double prime equal to m, and also get rid of the summation. Yeah. And yeah, so this is the numbers, and we also get rid of that, so we are left with the first register. That's this psi m dagger m, because m dagger become m, and okay, so we shouldn't have this here because we already used the summation. Okay, excuse me. And yeah, so we are left with the first register. So it's psi m dagger m prime, and the inner product with n big N sub m and psi. Okay, and yeah, so that's this thing. Yeah, and this is what we want, because this is the measurement probability of psi on the small n outcome, right? So yeah, so this is yeah. If you look back to our postulate of quantum mechanics, you see that this is the outcome probability of generalized measurement. Yeah. Do we write it somewhere here? Okay. Yeah, we have something similar here. This is big N sub n psi squared. Okay, and yeah, so you have big N sub small n psi and the square, so inner product with yourself. Okay, and also we want a post-measurement state. Okay, so post-measurement state will be this Pn on u psi and normalized. Okay, and Pn on u psi. Here once again we skip a lot of steps. Okay. And but Pn on u psi is equal to identity tensor is nm, and excuse me, identity tensor is projection on m, and on this u psi 0. So u psi 0 once again summation m prime, n sub m prime psi tensor m prime, and once again this n inner product with m prime give you delta function between n and m prime. So it's only equal 1 only when n equal to m prime. So you can get rid of summation m prime and just say m prime equal to m, and so this thing equal to n sub m on psi tensor m. Okay. And yeah, so that's what we get. Our state is n sub n on psi tensor n, and so we want to normalize this. Then you see that the norm square of those two things is well, the norm of those two things is the norm of this times norm of this, and norm of this is 1, so it's just divided by norm of this. Okay, so yeah, norm of n psi is this 1 over square root of psi and dagger n and on psi. Okay, and so you see that the post-measurement state is actually so yeah, so when you get some outcome m, the post-measurement state is actually product state once again. So we say that after we apply u, we get a very entangled state. Once again, after entangle u, we got this weird state. That's all the different weird M side tensor M and inner part and the summation superposition together is a weird entangled state, but after you do a measurement on M, it back to a product state. So product state is just a tensor product on one system with another system. Okay. So after you do a measurement, you back to a product state, and you see that in system Q, the state is exactly what you want is exactly the post-measurement state you want by doing a generalized measurement. And on state M, you get this computational basis state, and so now we got back to a little physics. So we hope that the physical system here will be able to, when you do this computational basis measurement, you can distinguish between those orthonormal state, and it will tell you which is this small n is, and and this small n will correspond to the outcome index of the generalized measurement you want to do. Okay, so here is a bit physical thing. You just hope your device are able to distinguish different small n, and so it's kind of a scale of your meter, and this meter result tells you the small n. Okay, sorry we are going a little over time. So you can ask questions during a break, and we'll take a 10-minute break now.这个是更 general 的事情，就是说 generalized measurement 也可以当做一个 inventory 再做一个 computational basis measurement， 但这个差别是你需要这个更复杂嘛，所以你需要 NCR system 的。对，通常需要 NCR。对。这下面就是应该没有算错。应该有写铃铛，那个我算错了，写错，抱歉。过去，这里应该有零。对，因为 U 是 joint 的，所以这里也要补零上去。对啊，原本的整个东西，这里要补零上去。呀，好多typo，抱歉。你说最上面啊，最上面是在算 post 那个，对，我在算数学公式的。因为 T_n 是那个 I tensor n 下面这里可以算对啊。然后还有一个地方的计算什么可是，应该。我等一把这个改变，但是我们在算那个，因为我们在算那个的时候，跟那个，像这个说，如果你用这个如果全部是这个的话，这个应该是考这个，应该是这个问题，他这样子没有就错了啊？没有啊。 因为这一个比较奇怪，就是 tensor 扩大之后，这一个它顺序不一定，我们从这个讲。
但是这个是 tensor 扩大吗？这个
零跟3是 tensor 扩大这个。
哦，我以为它是那个。哦，
不知道，他不知道，因为我们说两个 column vector 没办法乘法。
所以它是
它乘的话就用 tensor 扩大。
它其实中间是 tensor 扩大，然后 tensor 扩大比较大，那个它不会反。
它不会反弹，这样子。有 n 的话，基本上是有这样看，跟它存在，公募是包括。我做这个东西呢，那就是后面 calculate 用的事情，就是你说假设我们有一个 unitary， 我们要拼出来的感觉，后面会有什么？你的 case 是 universal 可以把它给提出任何，对啊，这种感觉。只是一个，对啊，这其实我们扯到 composite 这个话，你就可以想很多，就没有一个这件事情，这也只是一个存在性的证明，说存在一个你可以做这件事情。对啊，这有很多，就是什么2的，是多少？2的4方之类的吗？有点忘了，大风一说就，你们4的4方之类的，对吧？跳了一遍，终究还是看你的 n 是什么样子吧。我觉得，应该有，我没有特别想过，但是应该是有的。可能是看你的 n 长什么样子吧。但如果很奇怪的话，因为它还是蛮 structure 的嘛。比较 structure 的做法，我没有特别想过的。你是想要这样或者要讲efficiency吗？有一些我不知道什么 block encoding 之类的方法有没有比较简单就是。但我觉得你真的猜到 gate level 去看的话，说不定会有比那个直接暴力做简单的方法，就是应该会有，就是一些 control 的东西，但我不用太想。主要是这些 n， 因为他们就是看 m 的性质越好的话就越容易做嘛。例如它是 unitary， 或者是他们都是 projector 的话，m 不可能是 unitary，m 可能是 unitary。让他们接近几个小的 unitary 或者接近几个 projector 的。这样看，如果 n 都是 projector 的话就很简单嘛，你就写 control 之类的。
对啊，然后简化成下面。
对啊。然后可能现在再瞎想一些，大家比较喜欢猜的几个方法，有所谓的 block encoding 的方法，可能可以试试看。然后我可以乱写，但这只是乱猜的。block encoding，block encoding，到这样可以写。这里还可以写吗？反正design language 是很强的一个 block encoding。block encoding。这是个把个 matrix 塞进一个 unitary 的方法之类的。然后，如果 ni 可能可以想把上 police 说不定也可以吧。把它拆成不同的 poly， 然后再去做 control 的 poly 之类的，不知道有没有比较简单？不太确定。可能是把 encoding 方式决定。总之你想要做，我想要 现在这样把它做美。
第一章就有讲到的。哦，所以第一章就讲说 ，H 它就是一个固定的矩阵嘛。对啊。哦。这边就不要用。
哦 OK。好，可以了。
就是为什么它会这样？
我们说任何的 unitary diagonalizable matrix 可以先这样子，就是它这样子写，我说这是 eigenvector、eigenvalue 嘛，然后首先我们说它是一个 unitary diagonal，代表它的 eigenvector 都是 orthonormal to each other， 这些东西是 orthonormal， 这个是总之有证明的东西。
就是 AVI 会等于让打成 VI 嘛，没错。
对啊，然后所以这个缝我们要有这个缝会给我们 AVI 等于让的 IVI， 然后这个是因为把它拆开的话是
这个东西有所谓的反曲证或东西嘛？
哪个东西？
就是这个计算有反曲证嘛，反这边反左边要怎么让它只剩下 A？
等于让它
就是这边怎么变到这边的？就是 AVI 然后等于让它 VI 嘛，然后怎么变到 A 的？这个就是要怎么让左边等下 A， 就是把这 VI。
不是，我们要我们证明我们好像不是这里。这样逻辑有点混乱。但我证明说这个东西会给我们这个东西啊，就是如果用这个套进来的话，它会给我这个，然后所以 AVI 把 A 套进来，然后还等于这个东西啊，就是上 J VJ VJ 然后 VI。
这个东西是假设这样吗？还是？
这个东西就是它对，但是我们先假设它是这样子，然后试试看我们会得到对的结果嘛。所以 A 这个东西打到 VI 上面，然后我们要 I 跟 J 不一样，因为这是 dummy variable， 就是这里的上的这个 I 跟这里 I 不一样，所以我把这个改叫 J， 就上 J 让它 J VJ VJ， 然后在 VI 上面。对啊，这样可以吗？我在做计算。
可以问他。那这边这种是什么
？Cos measurement state 就是 measure 完的 state。
它不是你拿什么量测完了，它最后出来就是你量的东西啊。
没有量的东西会被变掉啊，就是 quantum measurement 都说你量了之后 state 会变掉，就是你会有不同的 outcome， 然后不同的 outcome 会对应有不同的 post measurement state。
就是你量完之后，它会有个结果，然后你的系统会
变掉，对，你的系统会变成这个东西。你有一个结果，然后相对的，你的系统会变得跟那个结果很像的一个 state。
好。对。那个结果的话，如果你再去量一次，会发生什么事情？
再量一次，以这种 measurement 来讲的话，就会得到一样的结果。因为它 state 就已经变成那个结果 state。
变成那个结果之后，你再怎么量都会出现一样的结果啊。
这句话有点复杂，就是如果是我们所谓 projective measurement 的话会一样，因为这 Pn square 等于 Pn， 但如果是 generalized measurement 的话，可能会有不同的结果，这样，就是后面的那个 mi 的那个东西可能会不一样。对，但是前三种 measurement 你一直量，它会一直出一样的结果。
对了，你 x 这样，你用0去量，它不是应该长这样吗？为什么会变这样？
不是，首先 x 不是 state， x 是一个 matrix 的。
对啊，它是一个，所以说 matrix 不能直接拿去量吗？
就是我们这里说量 matrix 的意思就是用这个来讲的。matrix 去量一个 matrix 的意思，其实是去量它的 eigenvector 的意思。
去量它的 eigenvector， 所以不能直接量矩阵，只能去量它的 eigenvector。
对啊，量矩阵就是量 eigenvector 的意思，那它的 eigenvector 是正跟负啊，所以就说是正的几率是多少，好像是负的几率是多少。
那这个，所以他是说用这个0的这个东西去量，然后得出来是1，那这个0跟1有什么关系？
没有关系。
没有关系。那我要
这个1是说 eigenvalue 是1。 说我量到 eigenvector 的时候是正的时候，然后 outcome 我是用它的 eigenvalue， 我说这个 outcome 就是我等于用 eigenvalue 来 label 它 outcome， 它的 state 会变成正的，然后它的 value 是这个正一，然后这是一个比较物理的说法，然后
对，所以说你用这个东西去量这个 x， 然后它有1/2的几率拿到正一。
对，还有1/2几率拿到负一，因为有另外一个。
对，这个正一跟负一就是因为上面这样的。
对。
这个 vector 的话，这个 S 矩阵它的 eigenvector 是这个正和这个负吗？
对啊，正跟负是之前有定义过的，然后可以想一下。
eigenvector 应该是只有一个吧，还是可以有两个？
有两个 eigenvector 啊。
不是，我说它不是应该就是一个东西，然后再加上一个矩阵嘛？这边怎么会有 F 线？
这个是一个矩阵，这是 projection on 的 eigenvector。
对，两个向量，为什么是两个向量把它乘在一起？
这是外积啊，这个是 row vector 乘以 column vector。
对啊，它不是
这个
向
向量
嘛？怎么会是两个向量？
它是这样子乘的啊，它是这个向量乘以这个向量。然后你要做一下矩阵乘法给我看吗？
它应该就一吧。
对啊，那它是1/2的1，所以两个向量乘在一起变成一个矩阵，因为它是 outer 夸大，所以它其实是 projection on 这个向量这样。对。
所以它是那个，这个笔不是我。
哦，抱歉。
这是特征值嘛？那特征向量是这个还是这个？
是这个东西啊。等一下，我向量写错了，抱歉。这样子的是数字，所以 k 的 vector 我们回到一开始东西圈 ，k 的 vector 是 column vector， 这个东西是这个东西嘛？然后我们写这个东西的时候是这个东西，然后2/2的这个东西。所以 eigenvector 通常讲的是这个吧 ？eigenvector 我们通常讲的是。
所以它是特征向量，它是特征值，那它是什么？
它是特征向量的 dual， 它就是特征向量写成 column vector。就是我们有定义过 dual 嘛？我们说，如果我们某个 psi 是，例如说是 A、B、C 这样子，然后我们定义它的 dual vector， 有个 psi 的 dual， 然后它是一个对应的 row vector， 每个 column vector 我们都对应一个 column vector， 然后它是其实蛮好写的。
这样好了，就像下面这个矩阵，你就把它拆成3个 eigenvector 嘛，然后前面再加一个 eigenvalue 嘛，那就是为什么？
对，我没写完。
好。
所以 dual 是这个 A star、B star、C star 的 vector， 所以每个向量我都可以这样定义。那当然你有更多就有更多，所以这个没有问题吗？
而且你要上课的话，就直接上课，就变多。你现在上课时间嘛，还是？
对。
这个
是差不多。这里放这里。抱歉。我们超过时间。Yeah, sorry for the late start. And any quick question on the composite system, generalized measurement on composite system, or I guess getting generalized measurement from composite system. And anyway, yeah. So here is a small summary of how do we do a generalized measurement by doing a projective measurement. That is, if we want to do a generalized measurement on a system Q, then you can first introduce an ancillary register M, that where you can where you are going to do projective measurement on. Then you can apply our special unitary U on our joint system Q tensor N. The U is a very entangling U is an entangling operation, and U will depend on what the measurement you want to do. Okay, and then you will do a computational basis measurement on your register M, and then you can get the outcome on this M. And after you do a measurement, then you can throw away this register M, and so your Q will get turned into the corresponding post-measurement state. So you will get outcome n, outcome small n, with the correct outcome probability of you doing a generalized measurement, and the post-measurement state will be this n sub n side. That's the corresponding. That's the correct post measurement state. Okay. Any questions so far? If not, then we can continue to more quantum protocols. Okay. So we have some quantum protocols that show us some powers of our quantum rule, those quantum mechanics quantum rules. Okay. And then the first application is what we call superdense coding. Okay. So superdense coding is this setup. So we suppose we have two bodies. Okay. So in communication, we usually call them Alice and Bob. Okay. For A and B. Okay. Alice and Bob, they live very far away from each other. And here their goal is they want to transmit data from Alice to Bob. Okay. And so we want to transform classical information. So classical information just encoded in some bit string. Okay. So they want to transmit from Alice to Bob. This is a very general setting, and you can imagine you can use this to do all kinds of things. Okay. And now come to the superdense part. Okay. So superdense part is so Alice has two classical bits, and so she wants to transmit to Bob with by sending only a single qubit. Okay. So here the catch here is we are able to do quantum communication. So we want to see whether quantum communication is more powerful than classical communication. Okay. So in particular, we want to transmit two classical bits by only sending one quantum bit. Okay. So yeah, so Alice is going to send Bob one state, that's the one qubit state, and one that at the end of the protocol, Bob will learn the two classical bits Alice want to transmit to him. Okay. And yeah, so this is possible. We can do it by using what we call so-called superdense coding. And sorry, another typo. And so you see the superdense part. So why this superdense is because classically basically you want to transmit one bit, then you need to send one bit. But quantumly, you can transmit 2 bits by sending 1 qubit, and this is perfectly. So in the protocol there is no error. So if everyone do every part perfectly, then yeah, Bob will get these 2 classical bits perfectly. Okay, so this is superdense coding, and let's see how this is done. So first step is we have a huge catch here. Okay, so we need to suppose that Alice and Bob, in addition to Alice being able to send 1 qubit to Bob, they actually have something else. So this is what called shared entanglement. Okay. So Alice and Bob need to initially share a pair of qubits that's in an entangled state. Okay, and so we have this psi 00 plus 1 1. Okay, and so we assume Alice and Bob just hold 2 quantum system already. So they're holding a quantum system that's already in this state 00 plus 1 1 over square root 2. Okay, they have this entangled state psi equal to 00 plus 1 1. And this is kind of assumption we didn't talk about previously, but we'll need this to do our superdense coding. And yeah, so here we have a little schematic. So we have this psi 00 plus 1 1, and assuming Alice for the first qubit, so means that this 0 is on Alice's part and this 1 is on Alice's part. And also Bob having this 0 and this 1. And once again, this is our composite system notation. So this is 0 0 is actually equal to 0 tensor 0, and 1 1 is actually equal to 1 tensor 1, but this is an entangled state, so this is not something tensor something. Okay, so this is a superposition between 0 tensor 0 and 1 tensor 1. Okay, and here we have a little bit of justification of why we think it's okay for Alice and Bob to share this state. Okay. And so there are several ways to get this state, and in particular Alice and Bob. So maybe Alice can create this state on her side and send one of them to Bob. Okay, but that will be a little bit of cheating. Then that means Alice already sent 1 qubit to Bob. But what's nice about this state is this state is just a fixed state. This means that this state doesn't depend on the message Alice is going to send. So remember, message Alice want to send is a 2-bit class information. So Alice has 2 classical bits she want to send to Bob. But this state doesn't depend on what Alice want to say. Alice want to say 0, 1, 2, 3, 4. Doesn't matter. This state is just 0, 0 plus 1, 1. Okay, it's a fixed state. And so maybe one way to see why it's good for being a fixed state is that this don't even need to be created by either Alice or Bob. So there is maybe some third party, maybe Charlie. Charlie can create this state on his side. So Charlie prepare 2 qubits in his side, and send the first qubit to Alice and the second qubit to Bob, and then Alice and Bob will share this state. So yeah, so here we just want to stress that having this state is kind of okay. It doesn't take out too much communication because this state doesn't depend on communication. Okay, and anyway, so that's enough for justification. We just assume Alice and Bob have this state. Now back to the quantum maze. So if Alice and Bob has this state, then what do they do to make Alice sending 4 bits of class information to Bob? Okay, okay, and so what is going on is so first Alice will do something on her part of the state. Okay, so remember Alice want to send 2 classical bits, and we can write the 2 classical bits in the 0 and 1. So maybe the 4 possibility are 0, 0, 0, 1, 1, 0, and 1, 1. So Alice want to send one of the 4 possible states. So Alice might start with one of those 4 messages, and she want Bob to know which one she holds. Okay, and so depending on the message Alice has, she will do different thing on her part. Okay, and so if she has 0, 0, then she does nothing, and she has 0, 1, and she do Z gate on her qubit. She has 1, 0, she do X gate, and she has 1, 1, and she do ZX, which actually means apply X gate, then apply Z gate to her qubit. Okay, and so what happened to her qubit is it will become those 4. Okay, and let's do one of the calculation here. Okay, to see. So this is where we see how the tensor product thing works. Okay, here's I guess a good example to see how the how the composite system calculation goes. So well, the identity obviously the state doesn't change, so it's trivial. So I guess let's see the Z. Okay, so what happened is Alice applies Z on her part. Okay, so we know Alice applies Z on her part. And then by our composite system postulate, Alice do Z on her part means that on the joint system, what we actually do is Z tensor identity. Okay, Z tensor identity, and or maybe in the subscript notation we can have Z on Alice and I on Bob. Okay, and so this is the thing we do on the joint state. Okay, and so what happened is we have so I guess back to the tensor identity. So this tensor identity acts on our starting state is 0, 0 plus 1, 1 over square root 2. Over square root 2 and 0, 0 plus 1, 1. I guess let's write this out in tensor product notation so it's a little more clear. Okay. And once again, we know 0, 0 is 0 tensor 0. Plus 1 tensor 1. Okay, and I'm trying to write this in nicer notation. Okay, and anyway, so we have the Z tensor I 1 over square root 2 0 tensor 0 plus 1 tensor 1. And now we can use the linearity. So we know this matrix multiplication is linear. So so this matrix multiply this vector, which can also be viewed as a matrix. So this matrix multiply on this matrix plus this matrix and on this coefficient, And the matrix multiplication is linear, so we can just take all this 1 over square root 2 and have product rule on those matrices, right? And so this is the tensor I multiplying 0 tensor 0 and plus the tensor I 1 tensor 1. Okay, and I auto space, so let's go up here. And so this thing is 1 over square root 2 still here. And then we just use our tensor product. Multiplication of tensor product is you have to do each register separately. So we have z on 0, tensor I on 0. Okay, so let's do this really slow. So this is z on so it's z on 0, tensor I on 0, plus z on 1, tensor I on 1. Okay, and finally we can do our multiplication. So z on 0 is just well, I on 1, I on 0, I on 1 is just 0 and 1. So I on 0 and I on 1 is just 0 and 1. And yeah, z on 0 is well, 0 is eigenset of z with eigenvalue 1. And so it's just still 0. So the first part is still 0 and 0, tensor 0. And so that's 0, 0. And then plus the second part. Okay, so z on 1. Now this is a little bit funny. So that's minus 1 of 1, where the minus 1 is a scalar. Okay, so remember z is matrix. Z is 1, 0, 0, minus 1. Okay, so z on 1 is 1 with a minus sign. Minus 1 and tensor 1. Okay. And we know that the tensor product, you have a scalar, then you can just put a scalar outside because the scalar on each side is the same. Okay, so this whole thing is, well, yeah, then you see that this whole thing is what we have here. So it's 1 over square root 2 over 0, 0, and minus 1, 1, because the minus comes from this minus sign here. Okay. So that's what happens when Alice do the z gate on her side. So Alice do z here, then you see that you basically do z on this 0 or 1, and the z on 0, still 0, z on 1 give you minus 1. Okay, and then you can, yeah, you should try this 1, 0 and 1, 1 yourself. And but to summarize this very fast, so basically what happened on this 1, 0 is Alice apply x on her part. Okay, Alice apply x on her part, and so what the gate she will do is x tensor identity. And what happened is x will add on this 0 to 1, and x add on 0 turns this 0 to 1, and x add on 1 turns this 1 to 0. And yeah, and you can see what happened when you apply x and z on this thing. Okay, any question? This is the hardest part of super dense coding, is knowing what happened to the composite system when you do gates on one part of it. Okay, so apply I or z or x or iy on her part, and the entangled state will turn into those 4 different states. Okay. And these 4 different states are famous because they are useful for all kinds of things. In particular, they are useful for super dense coding. But anyway, those 4 states are called Bell states. I guess here we can kind of mix up things. Okay, so they are called Bell state or EPR pairs. And I guess the basis composed of those 4 states are called Bell bases. Okay, and you kind of see from this name that important part of those 4 states is that they form orthogonal bases. And once again, this means that the 4 states are both normalized, this is a normal part, and they are orthogonal to each other. You can, yeah, I think this is also a homework problem. You can check that they are orthogonal to each other. And for example, I guess the one of the interesting one of orthogonal you can check is you can check 0, 0. Sorry, this 0, 0 plus 1, 1 is orthogonal to this 0, 0 minus 1, 1, because when you do inner product with each other, you have the inner product of this with this, then you have the 0 part give you 1, and the 1 part give you a -1, and this 1 plus -1 equals 0. Okay, and yeah, you can check all of them. There are 4 of them, so there are 6 pairs. You can check all those 6 pairs are orthogonal to each other. Okay, and yeah, and then we're back to what we know from measurement is that, or what we know from distinguishing quantum state is that you have those 4 Biot states. You have 4 states that are orthonormal to each other. Then they can be perfectly distinguished by a quantum measurement. In particular, you can do a quantum measurement. You can do the orthonormal basis measurement of where the bases are just those 4 states, right? You think about you have a 2-qubit system, then there is orthonormal basis, that's those 4 states, and so you just do the orthonormal basis measurement where the basis elements are all 4 of them, and you are perfectly distinguishing all 4 of them. Okay, and so that means we are very close to finish our protocol. So our protocol, so we say a lot of different things, but our protocol here is what we have done already is just Alice do something on her qubit. So depending on the message Alice wants to send, Alice do something on her qubit, and the joint state between Alice and Bob becomes those 4 states. And now Alice finally do the quantum communication. Alice now just send her part of the qubit to Bob. Okay, yeah. Alice send her part of the qubit to Bob, and Bob will have both of the qubit of those 4 states, 4 possible states. And that's basically the end of the protocol. Now we know that Bob has those 4 possible states, and but we know those 4 states are in orthonormal basis. So Bob can do orthonormal basis measurement. So this measurement in Biot basis, and then Bob will just determine which one of the states Alice has. And here we have a little more things about, a little more information about those 4 Biot states or EPR pairs. And in particular, so this one is called beta 00, this is called beta 01, beta 10, and beta 11, just corresponding to the 4 possible things that Alice can do. And yeah, we have a more mathematical form of beta XY here. And yeah, so that's the end of superdense coding. Okay, and I guess for now, any question? Do people understand how superdense coding works? Okay, yeah, once again, superdense coding is Alice and Bob start with sharing entangled state, and depending on the message Alice wants to send, Alice do one of the 4 things on her part, and that will turn this 2-qubit state into 4 orthogonal states. And we know that's totally fine because is a 2-qubit state. We know a 2-qubit state is a 4-dimensional state, so it has a 4 orthogonal state, 4 possible. Yeah, this 4-dimensional state has a basis of 4 orthonormal states. Okay, and once Alice turn the sharing entanglement to one of the sharing entangled state to one of the 4 possible Bell bases, then Alice just send her qubit to Bob, and Bob will have one of those 4 states, and Bob can distinguish which one he actually gets because they are all orthogonal to each other, so they are perfectly distinguishable. Okay, so yeah, superdense coding, and we want to talk a little bit about sharing entanglement. Okay, okay, and so first is a little more than EPR pair. Okay. And the EPR pairs are sometimes called maximally entangled state. Okay, and this this is a very informative name here. Okay, so we have maximally and entangled. Okay, so this name actually comes from there are ways to measure to quantify entanglement. Okay, so we so for now our entanglement is kind of 1, 0, or 1 thing. Is state is either entangled or not entangled. If it's not entangled, it can be written as a product of product state on 2 systems. And when entangled is not written as a product, but so it's a 0, 1 thing. But actually, there are more qualitative way to describe entanglement. So you can actually in particular for every bipartite state, you can actually calculate how much entanglement between them. Okay, and but we probably won't cover that in class. But if you do learn that, you will find out that those EPR pair, the amount of entanglement between them is the maximum we can get between 2 qubits. Okay, so yeah, if you want 2 qubits to be entangled, then those 4 EPR, those states have the maximum value. So they are also called the maximally entangled state. Okay, so that's a little more about entanglement, and then let's go back to this pre-shared entanglement thing. Okay, so I guess this is back to the justification we already talked about, but we just want to stress again. So pre-shared entanglement is kind of like cheating, because to create this pre-shared entanglement, you need to have some party create this state and send those parts to Alice or Bob. Okay, and so it requires some quantum communication for Alice and Bob to share this state. Okay, and yeah, that's actually something you can prove. If Alice has some quantum computation probability, Bob has some quantum computation probability, actually by only sending classical bit, you cannot create a shared entanglement between Alice and Bob. So you need to have some quantum communication to create shared entanglement between Alice and Bob. But that seems kind of cheating, but the nice part about shared entanglement is it doesn't contain information. So even if you only have quantum communication between Alice and Bob, so they can have, maybe they have some downtime, then Alice and Bob can just keep creating those shared entangled state. And then when Alice suddenly gets some message you want to send, she can use the shared entangled state they prepare in advance to quickly send her data to Bob by this super dense coding. Okay, so yeah, shared entanglement, they don't contain information about what Alice want to send to Bob, so it's kind of okay to create them beforehand. Okay, and then we go to something a little tricky. Okay, and so you can have a shared entanglement, and you actually have a similar idea classically, that is you can have shared randomness. Okay, so Alice and Bob, maybe they can throw some random coins beforehand, and then share the result with each other. Then they will have what's called shared randomness. And shared randomness will also create some correlation between Alice and Bob, but you can very easily show that shared randomness is less powerful than shared entanglement. In particular, the super dense coding is already approved. Okay, so if you have Alice and Bob shared randomness, and that means basically Alice and Bob can throw a coin together. They can jointly throw a coin or even several coins. So Alice can throw a coin and get random 0-1 outcome, and Bob will get a same 0-1 outcome. So that's a shared randomness. But with just shared randomness, it's not possible to do super dense coding. Okay, super dense coding is only possible if you have shared entanglement, and that shows that shared entanglement is more powerful than shared randomness. Okay, so just having correlation between Alice and Bob is not enough to do super dense coding. This entangled state, this quantum state is really more powerful than some similar classical results you can get. Okay, and but once again, this is shared entanglement. If you only have Alice and Bob, you find that you need to use 1 bit of quantum communication to create one EPR pair. If you only have, as we said, if you only have classical communication, you cannot create shared entanglement. Okay, and so because of these things, so because of basically those two things, you see, because shared entanglement is more powerful than shared randomness, and also you require quantum communication to create them. So you can actually think of the shared entanglement as some of the quantum resource. So some kind of quantum communication resource. So you can think about it as so this is something you can consume to make quantum communication do something more powerful than classical communication, right? So using the sharing entanglement, you can do super dense coding, particular. So with you consume one EPR pair and 1 qubit communication, then you see you can communicate 2 classical bit. Okay, and yeah, so that's sharing the entanglement. Any questions so far? If not, we have 15 minutes. So let's see if we can finish our other protocol. So that's quantum teleportation. It's kind of a reverse of quantum teleportation. Is kind of a reverse of super dense coding, as we'll see. Okay. So quantum teleportation basically want to transmit a quantum state. Okay. And so here we have a definition. So quantum teleportation is a technique to move an unknown quantum state around, and without actually physically moving a quantum state. I guess physically is a little weird, but without moving the thing that contains the quantum state around. Okay. So it's assume that you have some register at Alice and register at Bob, and so Alice has some quantum register, Bob has a quantum register, and between Alice and Bob there is no quantum communication, and so they only have classical communication, and Alice wants to have a state on her side appear on Bob's lab. Okay, and so that's quantum teleportation. Okay, so Alice and Bob, they are far away from each other, and they only have a classical communication, and they want to send a quantum state, and it's even an unknown quantum state. Okay, so if it's a known quantum state, you can just send a parameter to Bob, but it's an unknown quantum state, and you want to move this unknown quantum state to Bob's side. Okay, and so you think this is very hard because it's an unknown quantum state, and so if you just do major on it, then you will destroy the state, and you don't even fully learn the state. From the previous slide, we said that for unknown quantum state, you need many copies to do tomography to learn it. Okay, and so you cannot know what this state is. Then how do Bob know what is it? How do we let Bob get the state without just moving a whole state to Bob's side? That's how we use quantum teleportation. Okay, so we're going to send a classical message from Alice to Bob. I guess it's better to write Alice and Bob here. Okay, so the setting is we have Alice and Bob, and Alice is going to send a classical message to Bob. Classical. Okay, Alice is going to send classical message to Bob to let Bob learn his unknown quantum state. And that seems pretty unlikely because that's actually impossible. And once again, we need to use our shared entanglement. Okay. So it's a bit like super dense coding. So super dense coding, you send 1 qubit to send 2 classical bits, and quantum application is kind of reverse. You are going to send 2 classical bits to teleport 1 quantum qubit from Alice to Bob, and also using shared entanglement. Okay. So once again, we'll assume Alice and Bob have a pre-shared some entanglement between them, and they use that to teleport something from Alice's side to Bob's side. Okay. So let's draw the system a little bit. So we have Alice and Bob has shared entanglement, so 1 qubit on Alice, 1 qubit on Bob, and there is actually an extra qubit that is unknown quantum state phi, and at the end of the protocol, this side should appear on Bob's side. Okay. And so let's see what is quantum teleportation protocol. Okay, and it's a bit complicated. So the protocol do like this. So we are just going to do a very mathematical description of the protocol. Okay, and the protocol start with Alice has this unknown quantum state psi. So A0 plus B1, so we just have arbitrary A and B that have whatever normalization needed. Okay, so here we just have A and B here to parameterize our totally arbitrary unknown quantum state psi. And then we also say Alice and Bob share entanglement, so there is some share entanglement state beta 00 here. And yeah, so the state of the joint system, so the Alice side and Bob side, so there are totally 3 qubits. I guess let's draw this here. Okay. Once again, so there are 3 qubits in this system. Okay, Alice and Bob. And so they have a shared entangled state, so it's EPR here, and unknown psi here. Okay, so psi is A0 plus B1, and they have an EPR pair here. So EPR pair is 00 plus 11. Okay, and yeah, EPR pair is 00 plus 11, and so first qubit on Alice side. So the whole state is A0 plus B1 tensor 00 plus 11 times 1 over square root 2. And so you can multiply this all a little bit, then you see the state is A0 tensor 00 plus 11 plus B1 tensor 00 plus 11. And this 00 is, and this 01, and this 10, and this 11 is on Alice side. And this is 0, and this 1, this 0, and this 1 is on Bob's side. Okay. And so the starting state is a 3 qubit state. There are 3 qubits in this system. And so Alice is going to do 2 things on her side, and it's basically measuring in the Bell basis, but let's do this step by step. Okay. So Alice is going to do a CNAT gate and Henry gate on her side. Okay. So CNAT gate is actually a classical gate. It's a gate where, well, if you write it in the it's a 2 qubit gate. So if you write down the 4 by 4 matrix, it is 0 0 and 0 1 1 0 gate. And what this gate means is that it has a control qubit and a target qubit, and you will add the control qubit to the target qubit. Means that if the control qubit is 0, then this gate will do nothing, and if the control qubit 1, it will flip the target qubit or apply the NOT gate on the target qubit. And so we can see what happened here is that okay, and so we have a control qubit and a target qubit. So control qubit is 0 or 1, and target qubit is 0 1 or is 0 1. So as we say, if the control qubit is 0, it does nothing. So this A00 plus 11 is still A00 plus 11. And if the control qubit is 1, then we'll flip the target qubit. So control qubit is 1, and the target qubit from 0 0 and 1 1 become 1 0 and 0 1. Okay, and then once again, remember we have our tensor product rule. So the CNAT gate is on the first qubit, 2 qubit, and its identity on the third qubit. So actually, what happened for this CNAT? So we can have a CNAT, maybe we say it's 1 on 2. It's actually on the 3 qubit is a CNAT tensor identity, right? So CNAT tensor. So this thing. So actually, the thing we do on the 3 qubit is CNAT tensor identity on the 3 qubit, and we can think about CNAT 1 and 2 on tensor identity, and this thing. Let's not write this CNAT tensor identity, and for example, this thing acting on 1 1 0, and then we'll have a CNAT on 1 1, and you will keep the control qubit the same, and as we say, we add the control qubit to the target qubit, and this is actually XOR, so 1 plus 1 equals 2 equal to 0, okay, and this and 0 stays 0, okay. And so the CNAT 1 and 2 turn 1 1 0 to 1 0 0. Okay, so that's how we get this 1 1. Sorry, this is not the actual example we have. Okay, So it will turn 110 to 100, and but what we have is 100, and they will add this 1 on 0, so it becomes 110. Okay, so that's the C9 control on first qubit, target on the second qubit. Okay, so it will turn 100 to 110, and it will turn and similarly C0 tensor I 111 it will equal to 101, because the control on 1 you flip this 1 to 0. Okay, so that's what the C0 do, and our state becomes this state. So A0 of still 0 0 10 plus 1 1, and B1 over 1 0 plus 0 1. Okay, and the next thing is Alice is going to do a hit market on her qubit. Okay, and hit market, that's as a reminder here, hit market equal to 1 over square root 2, 1 1 1 minus 1, and in particular hit market flip between 0 1 and plus minus. So hit mark 0 equal to plus, and hit mark 1 equal to minus. And here we just do brute force calculation. Okay, and so hit mark 0 equal to plus, so this 0 here becomes a plus state. Sorry, these zeros here become plus state, and so that's 0 plus 1 with h1 over square root 2, and 0 on 1. Sorry, hit mark on 1 becomes a minus state, so this is 0 minus 1, and changing the normalization. Okay, so phi 2 is just changing here to 0 plus 1, here to 0 minus 1, and here is still 0 0 plus 1 1, here is still 1 0 plus 0 1. And then we just multiply by everything. Okay, once again, tensor product is tensor product is, so remember here is tensor product, here is tensor product, and here tensor product is a distributed law. So it's just 0 0 0 plus 0 1 1 plus 1 0 0 plus 1 1 1, etc. And we group things together by what happened to the first two qubits. So first two qubit is 0 0, then you have A 0 0 0 here. So you have 0 0 10 times A 0, and another 0 0 is here. So you have 0 0 1 and times B here. So you have a B1 here. And similarly for the 0 1 component, you have 0 1 with a 1 here and an A here. So 0 1 tensor A1 is this term, and then you have a 0 1 0, so B0 here, and yeah, you can you can similarly do other terms. So you see that there are 8 terms here, and there are 8 terms here, and then you check that. Hopefully we didn't do typo here. Okay, yeah. So we have those different states. Okay, so this is psi 2, and we return in terms of what are on the first two qubits. Okay, so 0 0, you have all 4 possibilities: 0 0 0 1 1 0 and 1 1. Okay, and finally the second part of the protocol actually shows why we want to write it this way is because the next part of the protocol is Alice is going to measure her 2 qubit. Remember, first 2 qubit is on Alice's part. So Alice is going to measure her first qubit, and in computational basis. So computational basis is a 0 state, 1 1 state, 0 1 1 0 1 1. So basically she will do, okay, and so yeah, and as we say, in composite system, what we will do is we are going to project the first qubit into either 0, the projector onto 0, and the tensor I3, and 0 1 project on 0 1 tensor I3, etc. So doing those projector, but we already write these first two qubits in this basis. So what happens is you will get some probability of getting the 0 when you project on 0 0, then yeah, then you do project on 0 0, then this component will single out. Okay, Okay, so you project on 0, 0, you do this 0, 0 project tensor I3, then your post measurement state becomes the 0, 0 tensor A0 plus B1. And you need to normalize it actually with a 1 over 2, but you normalize it, you will find out that the normalization constant is just this 1 over 2. You just get rid of this 1 over 2 and it is normalized. Because this has norm 1 and we know AB is normalized, so this A0 plus B1 is normalized. And similarly, if you get the 0, 1 outcome, you see the post-measurement state is this 0, 1 over 2, 0, 1, A1 plus B0 normalized, which is 0, 1 tensor A0 plus B1, and similarly 1, 0 for 1, 1. And actually, from where we say the normalization constant is 1 over 2, we know that the measurement probability are all 1 over 4. And we are over time, so let's say very quickly what Bob will do and just close up here. And so we are very close to what we finished. So Alice knows this 4 measurement outcome, and Bob will get those 4 states kind of like the state Alice get. And what Alice will do is Alice send the measurement outcome to Bob, so send the result to Bob. Okay. Alice will say, I have either 0, 0 or 0, 1 or 1, 0, 1, 1 here. So tell Bob that I have those states, and Bob will know which one of those states he has. So maybe Alice and say, I measure 0, 1, and Bob know his state is A1 plus B0. And if Bob know he has A1 plus B0, then he can just apply X on A1 plus B0. And that will turn the state into A0 plus B1. And for 1, 0 and 1, 1, Bob can do different correction. That we'll check next time. Okay, yeah. And so that's the quantitative application protocol. And we'll continue on next Tuesday to finish the description and some discussion on that. And so see you on next Tuesday. Sorry for going over time. Okay. 作业
可以这样去。
哦，对，哎，作业2还没有丢，对不对？
是吧？
作业没有，作业我想改一下wording，就是我们先把。